My 11th standard warriors, welcome to the last chapter of your 11th standard JEE Physics, and that's waves. And if you guys are thinking waves is what is on your screen, then you guys are a little bit mistaken. So we're going to talk what exactly waves is, what the equation looks like, and we're going to understand the different terms and calculate them for waves. So all of this with me, Shreyas, your physics master teacher at Vedantu, going live. Hello Ankit, Vishwant, Emmanuel, Nathi, Nagraju, Srinivasa Rao. Hello Kartika. Nice to see you all here. Welcome to lecture number 1, Nurture series on Enthuse, your dedicated English medium channel for JEE, KVPY, BIT, SAT, and you name it. And in today's session, we are going to see the different kinds of waves. We are going to classify the waves. We're also going to see what's the equation of a wave, and we're going to see the equation for transverse as well as the longitudinal wave. And then we are also going to talk about the general equations, and we are going to see some graphical analysis as well. And yes, we're going to end the class with pressure, amplitude, displacement amplitude, and waves on a string, of course. So all of this with me, your captain. Hello Kavya, hello Kailash, Vishwant Reddy, good evening Ishpreet, thank you for the hearts, thank you Aishwarya for the hearts as well. I hope you guys are doing well. Are you guys geared up? Last chapter, 11th standard, here we go. It's been a long journey, and after this, I'm going to come up with problem solving, strategy sessions, and what you should do in case you have backlogs, and how you can prepare for JEE Advanced, JEE Mains, and the other examinations. Because it's not just about completing portions, it's also about strategies. So I'm going to come up with all of it for you. So stay tuned on this channel, and that's the reason why you should hit the like as well as the subscribe button. And not just that, when you hit the like button, it also gives us the motivation to conduct more such amazing classes for all of you. And also YouTube algorithm, the way it works is our lectures will pop up on your feed. Thank you so much for all your support till now. Hello Shrivashini, Ganesh, nice to see you all. Hi Gandipali, Dakshin, nice to see you back. Hi Vanita, hello Tushar. Good evening Bachalog. So let's begin with a small quiz. With reference to waves, what exactly is a disturbance? Okay, alright Ankit, if you're not able to manage time for the left subjects, well, for the 12th standard, maybe you can be little bit more specific in what way. Hi Natasha, hi Pavi, hi Kartika. Okay, Emmanuel saying option A. With reference to waves, is it that the disturbance refers to the resistance produced by some particles? Is it referring to the oscillation produced by some energy that creates a wave? Is it referring to the wavelength, or is it referring to the speed of the wave? Okay, many of you are saying option A. Hello Neha, good evening. All right. So there we go. The correct answer is not A, it is actually B. It refers to the resistance produced by some particles of a material. Is that what a disturbance is? Well, there are different kinds of disturbances. Like in a class, if you remember, if somebody is making noise, that's a disturbance. But with regards to waves, disturbance is something which is created by the source and it transfers energy from it via the medium, or maybe medium is also not needed in certain cases. So some kind of vibration, some kind of disturbance which is created by the source, it produces some energy, and that in turn creates a wave. Yep. So Shrihar Darshani, for understanding this chapter, you should be strong at simple harmonic motion. That's the most important thing. Yep, it is important, Abhinjoy, for both mains as well as advanced. Alright, Raghav, I'm not able to find your Instagram chat, bacha. If you can message me what is your, or comment on the previous video, what exactly your Instagram ID, I can probably look for your Instagram message. I'm not able to find your message only. I tried so much. Alright, so hello Molesh, hello Bini Joseph, welcome aboard. So I hope this is clear. Moving on to the next one. Which of the following is wrong? Which of the following is wrong? Let's see. Sound travels in straight line. Sound is a form of energy. Sound travels in the form of waves. Sound travels faster in vacuum than in air. Okay, let's see how many of you can get this. Hi Nitya. Sashank, I'm very good. Join in. We just started few minutes back. You can rewind back the session a little bit, even in a live class. So don't worry, even if you're joining in now. Okay, Naveen saying C, Ankit saying D, Karthikeyan saying A. Amey Difle say hello, hello, hello. Well, the correct answer, most of you are slightly correct. Some of you got it wrong. The correct answer is sound travels faster in vacuum than in air is obviously wrong. Well, sound travels in a straight line unless and until it encounters an obstruction. Yes, it will travel. It's like any wave. Any wave will travel in a straight line path unless it encounters there is a condition. Okay, sound is a form of energy. Yes. So sound transmits some energy. Your speakers, they have some wattage written over it. This many watt speaker, that many watt speaker. So obviously it has some energy. Sound travels in the form of waves. Yes, sound is a wave. Sound cannot travel in vacuum. I'm pretty sure you would have heard about that statement or that fact that you cannot talk in space, in vacuum. When you're outside the atmosphere, you cannot talk to each other. So two astronauts cannot talk to each other even if they could survive without their spacesuits. So understand, there is no atmosphere. You need some kind of a medium. So sound can't even travel in vacuum. So there is no point of describing about its speed. Yes, Shashank, SHM is completed last month itself. All right. Now, Mitesh, this channel is more devoted towards JEE, KVPY, BitSat, all of that. But yes, we will have some kind of a NCERT revision, but these sessions will help you with NCERT as well. In fact, boards. Okay. In fact, it is more of higher level than boards, but definitely you will get a lot and gain a lot from these sessions, even for boards. So only on Earth sound waves travel. Yes, Tamil. In case even if there is a planet with some kind of atmosphere, even there it can travel. So it needs something. Sound needs some masala, some material. Without that, it can't travel. So what is a wave? Many students keep asking me this question. So let me put forward this to you. See guys, look at this. I always give this example because this is a beautiful example. Imagine Pandus standing in a line. These are all Pandus standing in a line. Okay, I don't know, they could be waiting for something, maybe for a movie or maybe for, some maybe booking, God knows. Maybe they are booking some ticket of a movie, maybe the latest movie, Pushpa. So there is a Pushpa movie, P-U-S-H-P-A, Pushpa movie going on. So every Pandu is waiting over here in line to watch that movie. They want to buy the tickets. Imagine they get restless. They want to watch that movie eagerly. All right, because all of them have their favorite superstar, Allu Arjun, out there, right? So what this Pandu at the back does, he pushes this Pandu falls on this Pandu, 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 and so on and so forth. So the last person, when he pushes this Pandu, these Pandus keep on falling like dominoes. They keep on falling, tuck, 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 tuck. These Pandus transmit the energy from here to there, from here to there, without they themselves having to go from A to B. Remember, any of these Pandus, whether you take this or this Pandu, none of them travel from this point to this point. This is our source. This is our destination. None of these Pandus traveled, but they transmitted the energy. So wave is nothing but transmission of energy from the source to destination, or it's just created by the source. It spreads in all the directions. Is that understood, my warriors? So what is a wave? Whereas when this Pandu, he himself goes running and hits on that counter, that is particle motion. If this last Pandu goes running and hits on that counter, that is particle motion. But if this Pandu pushes these people, then that is wave motion. So there are two ways in which energy can be transmitted. Okay, so there are two ways in which energy can be transmitted. One is particle, one is wave. Wave mein, you don't have the particles themselves moving. The particles maintain their position on an average, but it's only the energy which goes from one point to the other. So this is another good example. You take a string and you create a pulse. You have a string or a carpet. You would have seen Tom and Jerry. Tom lifts the carpet and brings it down. That big pulse follows Jerry. You might have seen Tom and Jerry, I hope. And in case you haven't, this animation is a good way of seeing how each point on that wire is at the same place, but the energy is getting transmitted as such. You can see that the energy is moving. Nothing as such is moving from left to right. Only the particles are moving here and there, but maintaining their position. So what are the different modes of energy transfer? Modes of energy transfer. Like I said, particle and wave. I have explained this to you. But a wave also can be classified into further categories. One is called mechanical. Second one is called non-mechanical. Keshav, definitely bacha, this is a lecture 1 of waves. Okay, very good KNMS. Alright, so mechanical and non-mechanical. What is the meaning of mechanical, non-mechanical? I'll come to it in case you have forgotten. And mechanical also I can classify into 2 further types, transverse and longitudinal. Usually the non-mechanical waves we talk about are transverse in nature. We'll talk about what these definitions mean. So let's get started with these definitions. Okay, first let's talk about what is mechanical, what is non-mechanical. Look at this diagram, look at this diagram. Look at this diagram, look at that diagram. Hi Nikhil Krishna. See, in this kind of a wave, the disturbance is traveling. You can see that the disturbance is traveling, but the particles maintain their position. The particles collide with each other. They transmit their energy from one point to the other. The particles are carrier of energy. There is some solid, liquid or gas involved. So when there is some solid, liquid or gas involved, which acts like the carrier of energy, just like a train is the carrier of passengers from one city to other, the train is the medium. Here, solid, liquid or gas is the medium. That is called as the mechanical wave. Examples will be sound. Like when you talk, the sound which travels, it needs air. Without air, it cannot travel. So sound is a mechanical wave. Whereas, if you talk about this category over here, you can see that this is actually an electromagnetic wave, which is light or radio waves or the mobile waves or the Bluetooth waves. You might say, sir, the Bluetooth, the radio waves, they're traveling through air, sir. So it needs medium. No, no, no. It happens to travel in air, but it's not like if air was not there, it won't travel. It will still travel. It's just that air also it can accommodate these waves. There is no issue in that. Just that the speed of the waves will change depending on the medium, but it can still propagate. In fact, these waves do not need medium. They do not take the help of the medium for their propagation. But yes, their speeds can get affected because of the presence of a medium. As such, their propagation is not stopped because of the medium. I hope this is clear. Is that understood? What about headphones? Headphones is not a wave. Headphones create sound which is nothing but a mechanical wave. I hope that is clear. So, I hope the difference between mechanical and non-mechanical is very obvious now. So, the vibrations produced by the strings of a guitar or the vibrations produced by your vocal cords, or you take a string and create some pulses, those are all mechanical waves. Your radio waves, then your matter waves which you have learnt in atomic structure, de Broglie wavelength in your chemistry hopefully, those are all basically non-mechanical waves. They don't need mechanical medium for their propagation. Understood, my warriors? Hi Ritesh, good evening. Alright, so moving ahead. Next classification, transverse. Guys, what's the basic definition of transverse? I'm very good, Ritesh. Yes, Vikneshwaran, that's happening in Pathfinder. This is Nurture. Nurture series is for 11th. In 12th, you will have communication, semiconductors, atomic physics, all of that. That's happening tomorrow, next week, all of that. Perpendicular. Yes, exactly, Gokulnath. Perpendicular. So, remember I had told you the particles maintain their position, but they can move around a little bit. And when they move around, there are 2 ways in which they can move. One, they move perpendicular to the direction in which the wave is moving. That time, perpendicular, that is called as transverse wave. So you can see the particles are going up and down. The wave is going left or right. The wave can go left or right, or the wave could be going up or down, and the particles could be going left and right. The motion is always perpendicular to the wave. That is called as transverse. Longitudinal, long, along. That's how you can remember it. Along the wave, longitudinal. So if the wave is going that way, then you will see the particles will have their motion along the direction of the wave. Along the direction of the wave. Those are called as longitudinal waves. Come on, think and tell me, if I take a string and I generate a wave, what kind of a wave would it be? Would it be transverse or would it be longitudinal? Similarly, think when I talk, the sound which is traveling, is it creating a transverse wave or a longitudinal wave? Put it up in the chat box. Yes, Muthuram, definitely you can join. Alright, so, well, in case you're still confused, look at the simulation. This is a wave on a string. You can see that right over here. This is a wave on a string, right? And how are the particles moving? The particles are moving up and down, and the wave is going right side. This is obviously a transverse wave. Look at this spring. The particles of the spring come close and go far away. They are moving along the direction of the wave propagation. This is a longitudinal wave. So you can take a long spring and create a sudden compression. You will see the compression will go. Same thing when you talk, the particles go back and forward, okay, along the direction of the wave. So the sound is also a longitudinal wave. Fair enough. Let's see if you can answer this question. The propagation of a longitudinal wave through a material medium, the quantities transmitted in the propagation direction are, which of these quantities do you think are transmitted in the direction of the propagation for a longitudinal wave? Let's see how many of you can answer this. Narayan, this is not one shot. These are in-depth detailed classes. So you can think of it like one shot for wave equation and type of waves. Yep. And then again one more shot for the wave speed and intensity and energy next class, and so on and so forth. By 2 weeks we'll be done with this chapter. So by next week or so we are done with this chapter. Alright, cool. Let's see how many of you can get this. Some of you are saying A, some of you are saying D. Alright, Aishwarya going with D, Gokulnath going with D, Neha also going D, Nandini going with A, Prakash saying D, Karthikeyan saying A, Varalakshmi is saying B. Interesting. In longitudinal waves, which of these quantities move in the direction of the wave? Longitudinal. Guys, it can't be mass. The mass never actually moves in the direction of the wave. Yes, there is motion, but understand, it is not transmitted. It is not transmitted. Understand the meaning of the word transmitted. Many students will make a mistake here. Transmitted means, oops, let's go back. Yep, transmitted means over here, it should travel from point A to point B. The mass of that particular medium, it just keeps oscillating. It just keeps oscillating back and forth. It does not transmit from one point to the other. Momentum and energy both will travel. You will see the momentum will get transmitted. Remember that example of all the pandus standing in a line? When you push one pandu, they fall like dominoes. Isn't the momentum also getting transmitted from this point to the other? Yes. So momentum will also go, energy will also go. So it's like one ball connected to next, connected to next, connected to next. So the momentum continuously gets transmitted from one to next to next to next. Is that clear? I hope this is understood. Alright. Purvi Bhakta, you missed a little bit, maybe 10 minutes or so. Okay, 10-15 minutes. So just rewind back, quickly catch up at 1.5x or 2x speed. That option is available on YouTube. Very good. Alright. So let's get moving to the next one. And here it is. Before we go ahead, let me also give a quick update, because there is some important thing which will end tonight. Many of you do not know that. Remember, Vedantu, which is probably very well known to everyone, but some of you probably are worried, sir, can I actually crack studying online? Well, yes. Let me show you two things. There were 1,500 students last year who cracked JEE Advanced. There were thousands who cracked JEE Mains, and they got amazing results. When I say crack JEE Mains, That means they got amazing percentiles. You can see the number of students above 90 percentile. It's 3,000 plus students, and there were more. You know, if you start counting the students who registered towards the end, and probably some of them did not even, you know, share the results or something like that. There are so many students who have cracked JEE via Vedantu, via online learning, and all of this you can also take up sitting at home using an offer on Republic Day, and that's 50% off. The Republic Day offer, it's going on for this entire week. You can call it the Republic Day, Republic Week offer, 50% off. All the courses are available at maximum discounts. Go ahead, check it out in the description box. The links are there for joining 11 to 12th, 12th standard crash course, droppers batch, anything that you want to join. Check it out. Use the coupon code so that anything goes wrong, you can definitely get in touch with me then. All right, moving now to the next point. General wave equation. So what is displacement wave? Displacement wave, well, not sure, Gokul-nath, what exactly you mean by that displacement wave. Is it some specific type or some specific thing that you have studied in context with something? Can you elaborate on that? JEE Mains 2022, Nara, nobody knows when it will be conducted. Now, wave equation. See, when a wave on a string travels, look at this graph, look at this graph. The upper one is a photograph. The upper one is a photograph. Here, you can notice each point on that string has a different y coordinate. Do you see that? It has a different y coordinate. So, if I choose some x value, it will have some y. If I choose some other x, it will have some other y. Some other x, some other y. So, the y coordinate depends on the function, or is a function of x. Everybody agrees with this? Wave and oscillation, yes, Karthikeyan, definitely there is a very big relationship between both of them. Wave and oscillation, you can see so many terms will be similar. You will notice that when I write the wave equation. So, I can easily say y is definitely a function of x. But not just that. Look at the bottom graph. If I stick at 1x and I go up, I notice that the particle keeps moving up and down with time. You take any particle, let's say a particle here, you can see it keeps going up and down. So the y coordinate is not just a function of x, it is also a function of time. So can I then say, combining both of these things, that the y coordinate is actually a function of x as well as t? X as well as t, everybody agrees with that? Now I will label these variables. Observe this. What is y called? Y is called as the transverse displacement. It is called as the transverse displacement. Why is it called as the transverse displacement? You can see it very clearly from here. Any point over here will have some displacement in the vertical direction, in the transverse direction. So this is your y, your transverse, perpendicular displacement. That's what y is. X and t are your coordinates on that string. X and t are coordinates on the string, and t is time, obviously. So this is nothing but the mean position. This is the mean position of the particle that you are talking about. Why am I calling it as the mean position? Because if there was no wave going over the string, this particle would be here, which is exactly the position of such a particle. This is that coordinate x which I am talking about. This is where the particle would be without the wave. And t obviously stands for the time at which you are looking at it. Fair enough? Very good. Yes, Narayan, I have covered SHM long time back. Now, here is the challenging part. Does any function as a function of x and time represent a wave? That's what we are going to focus. And for that, let me bring a graph on your screen. So does any function as a function of x and t give you a wave equation? Let's try this out. Let's say I write something, y is equal to, I don't know, 2 into, let's say, x, and let's say square maybe. Okay, let's see if I have a function. Yes, 2 into x square. Look at this. This is a graph which is like a parabola, and let me also add some t over here, maybe like this, maybe t. Okay, and I'll put up a slider. Okay, this is a very, very interesting graph. Okay, let's see what happens. X square t square. Y is equal to 2x square t square, and I'm going to change the value of t, okay, from, let's say, 0 to 10 in the increments of 0.1, and let's see what happens. Okay, this is how the graph works, and let's see what happens. Oh, look at this, the way the graph is changing. Observe this. The graph is expanding like that, and it is coming back like this. Does this look like a wave to you? Does this look like a string on which a wave is traveling? Answer this. Oh, it's a parabola which is like going back and forth. Why is that happening? Because there is t as well. There is t as well in this. You can see there is t as well. Y is a function of x, y is a function of t. So both x and time are changing. Definitely it's not a wave. Let's try something else. Maybe I'll put up a plus or something and see what happens. Okay, I'll put up a plus. Okay, let's see what happens. Oh my god, what the hell happened? Look at this. Okay, where is this parabola even going? That parabola just went out of the screen. It just wants to go off. Look at this, the parabola went off. Is this a wave? Definitely not. This is also not a wave. Why are we using quadratic? I'm just putting up some equation. There is no need of quadratic. I can put something else also. You don't like this? No issues. Let's put sine function and see what happens. Let's put some sine function. So I'll put sine, and let's say I put x into t, and maybe I can do anything. Okay, I can just put some values out here. So let me put x square, t square. I can put cube as well. Okay, I can put cube as well, and let's see what happens. Is this like a wave equation? Definitely not. You can see this. This is definitely not a wave equation. This is like something crazy is happening. This is not a wave equation. Right? Now, here is what I'm going to do. I don't like all this. So probably let's go back to something very simple. I don't want to keep cube and all because the graph will change very fast. What about this? I'll change this to something, probably like this. Look at this now. X minus t, and I will just see this, how it's going to look like. X minus t, and yeah, something maybe square or cube, doesn't matter. Oh, look at this now. Look at this. Look at this. Look at this. It's crazy. Look at this. Parabola is moving. Did you see that? Is this now looking like a wave? Yes or no? Put it up in the chat box. Hi Abhishek. Is this now looking like a moving wave? Does it? Yes, it does. Very good. Very good. Now, excellent Dakshin. Very good Karthikeyan, Ayush. Very good. Very good Kailash. Now let's say I make it something else. Maybe you're like, sir, it is quadratic, maybe that's why. Let's make this, I don't know, maybe raised to 5. Oh, look at this. This is also like a wave. It's traveling on that string. This is also like a wave. Yes, it is traveling. Okay, let me change the constants and see what happens. Maybe let's make this as 3 and let's say make this as 2. Does it change anything? No, it's still moving. Interesting. Let me change the power. Maybe I will make it cube and see what happens. Let's say if I make it cube, then what happens? Oh, it is still going. Definitely it is going. You can see that it's like a wave which is traveling. Interesting. If I make it square, yep, it is going. Definitely it is going. You can see that. It is definitely going from left to right. Okay, interesting. What if instead of minus, I put this as plus? Oh, now it starts going this side. Whoa, this is so cool. Now it starts going this side. Very good. Now I start getting ideas. This just tells me that this function is something x plus something t. That's it. Something x plus something t. Now, if you make it infinite, Abhishek, obviously it will become like a straight line. That curviness will go off. It will become very steep. I don't want to make that. Okay. What if instead of this I make it as sine? Let's see what happens if I make this as sine or cos or something. Let's see what happens then. Okay, I'm just going to put cos or sine. Okay, and see what happens. Okay, perfecto. Whoa, this is also a wave. Did you see that, my warriors? This is also a wave. Now I get ideas. Now I start getting ideas. This means any function which is of the form something x plus something t is going to look like a wave equation. The moment I change the power, let's say I make this t cube or something, let's say I make this t cube or t square or something like that, now it is not a wave. Like, sir, it is still a wave. No, it is not a wave which is going at constant speed. The speed is changing. You can see that the speed, it's accelerated wave or something else. So basically it should be a linear relationship. It should be a linear relationship. Do you see that? 3x plus 2t. I hope everybody can see that. Okay, 3x plus 2t will work. Yep, it will work, definitely. Okay, fair enough. Very good, very good. So, another thing that you noticed, if this is a plus, the wave is going towards negative x-axis. If it is a minus, oops, sorry, let's make this a minus. And then what happens? Then it goes towards the plus x-axis. Perfecto. So that means I can also put some e raised to something as well. If you guys are thinking only this will work, no. Even something like e raised to x will also work. Let's say I choose some function like exponential. Where is, oh my god, it's little difficult to find those functions, but yep, I can keep an exponential function as well, and then also you will see that the graph will keep shifting, but you get the idea, hopefully. All right, so for now let me just keep it like this, and you can see that it is moving. So going back to our slide, okay, let's go back. So what did we learn? Not any function is a wave function. All the functions, all continuous functions of the form y is equal to some function of some constant plus or minus some another constant into time. These functions are wave equations. Should be some function of that, and examples I have just shown it to you. Also notice one important thing. If it is plus, then it is going towards negative x-axis. If it is plus, it is going towards negative x-axis. I just shown it to you. And if it is minus, then it is going towards positive x-axis. Is that clear, my warriors? Yes, that's Desmos. Yep, Gokulnath, it is, my friend. Okay, this is Nurture series, Tangudu. All right, and we have time. You have time in 11th standard. Don't watch one shots now. Okay, especially for 11th standard. Is that understood? Next thing that I want you to notice, let's go back to that graph. Observe this. I'm just going to probably change this manually, and I want you to see how much it moves, okay, in let's say 1 second. So let's just change this step to probably 1 second. Okay, just 1 second or 2 seconds maybe. Just put it 2 seconds. Okay, let's see how it looks like now. Okay, observe this, and I'll change these coefficients. Let's say I start it from 1 and 1. Now see, this is at t is equal to 0. The parabola is at the origin. Let's change the time. Let's increase the time, and let's make the time as 1 second. See where the graph has moved. See where the graph has moved. It has moved by 1 unit. So this is nothing but this point over here is 1, 0. Everybody agrees with this? Perfecto. Perfecto Tamil, Desmos is the graphing software. You can see that this is Desmos, the graphing software. Now let's change the coefficient. Let's make this something else, maybe 2x. Okay, let's make it 2x and see how much does this wave move by. Observe carefully. Okay, let's see where it is moving. All right, in 1 second. Okay, in 1 second, it has moved to 0.5. You can see that it's 0.5. Interesting. Okay, let's bring it back. Let's change this number, the coefficient of t, to maybe let's say 4 or maybe 6 or something like that. And let's see how much does it move in 1 second. Observe this. Time is increasing, 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 increasing. And there you go. It becomes 1 second. Okay, there you go. It becomes 1 second. It has moved 3 units. From these three things, can you now guess how much does the wave move per second or in 1 second? Think about it. Think about it. How much does the wave go in 1 second? Are you able to get a general idea about this? Are you able to see some generic correlation between all these things? See, this is 6, this is 2. How much has it moved? It has moved 3 units. If I change this 6 to let's say 4, it would have moved by 2 units. Interesting. So what is the relationship between this number here, and how much does the wave move by? You can see 4 by 2 is 2. If I, let's say, change it to something else, if I make this as, let's say, 1 times of t, 1 by 2 is half. So this moves by 0.5 units. That clearly shows that the wave speed, what was the wave speed? It was the coefficient of time upon coefficient of x. That means it is nothing but b by a. I'm talking about speed, not velocity. I'm just interested in the magnitude of it. This is b by a. I hope you guys get it. Yes, it is b by a. Understood, my warriors? Perfecto. Perfecto. This is something which you should know. So generic wave equation is of this form. Plus and minus you should know. Plus means negative side, negative means positive side. Wave speed is this one. Some of you will be also confused with one more thing. Let me add over here one more point. Some of you might think, sir, what if y is a function of bt plus minus ax? If I change the order, will it matter? No, it really doesn't matter. Whether you put bt plus minus ax or ax plus minus bt, it is one and the same thing. So this is OR. Okay, you can change the order in the graphing software as well, and you will see it really doesn't matter. I can put 1t minus 2x. Okay, if you play this, you will see it will still go towards the positive side. So the order does not actually matter. Okay, I hope this is understood. So it's just based on these coefficients of x as well as time. So this is a generic equation. Fair enough. Let's move to some questions based on this concept. Okay, I have put it up all for you in the printed form as well. Let's solve a question. Which one of the following does not represent a traveling wave? Out of these functions, one of them does not represent a traveling wave. Think which one it is. Figure this out. Figure this out. Come on, my warriors, think about it. D says Dakshin. What pi refers? Right now, pi do not worry about pi. Okay. Even if it comes somewhere, we are going to talk about sinusoidal waves separately. Don't worry about it. Okay. Then it's saying D lag raha hai. Okay. Okay. Interesting. Many of you are saying D. Looks like you guys are correct. And you guys are correct. Reason being, x square minus vt square. That is not the correct form. I just gave the correct form. It should be some function of ax plus minus bt. Individually they cannot have powers, but as a whole they can have power. Understand that. So notice over here, this is sine of something x plus minus something into t. Fine, this is okay. This something x something time, perfectly okay. This something x something time, perfectly okay. This is square, this is not allowed. This is not allowed. That's why option D is wrong. Got it? It should be always in the linear form. Please understand, if you have a function like this, 3 into 7x minus 2t whole cube, this is correct. It's not wrong because it is a linear function. You can square, cube, you can take square root of it also. That's also okay. This is also okay. But individually, you cannot do that. Moving to the next question coming up on your screen. Thank you, Anand. All right. The disturbance of a wave propagating in the negative direction is given by, okay, and this is that too at t is equal to 0. At t is equal to 0, let's say, or forget t is equal to 0, that is also not needed. Let's just write it down. Maybe a generic equation. I'm just going to give it to you randomly. 5 divided by, okay, maybe 2 plus, let's say 3x minus, it's going in the negative direction. If it's going in the negative direction, that means I need to put a plus. And let's say I have 6t square. Very interesting equation. Let's see how many of you can think how the wave looks like in your sketchbook, in your rough book, in your notebook, whatever you are using right now. I know you cannot post the answers online right now. Obviously, it is like sketch the wave. So let's see how should it look like. In order to solve these kind of questions, what you should usually do is try to see how the wave looks like initially. See where it is, how it is initially, and then think what should happen next. Observe. Let's say, for example, let's say at t is equal to 0. That means at t is equal to 0, you have taken a photo, you have taken a snapshot. Let's see what it looks like. So y0 will be nothing but 5 divided by 2 plus 3x plus 0 whole square, which is nothing but 5 divided by 2 plus 3 square is 9, 9x square. So that is what y0 looks like at time 0. Now you need to visualize how would this function look graphically. That's why you should be strong at graphs. So try to substitute certain values and probably you will get a hang of it. Let's say I draw this as my y-axis and this as my x-axis. Okay, this is your y, this is your origin, this is your x-axis. Look at it. When x is 0, 9x square is 0, y will become 5 by 2, which is 2.5. So initially when time is 0, x is 0, you can see the y value is 5 by 2. 5 by 2 is 2.5. So maybe 2.5 is somewhere over here. Okay, so this is 2.5. Now, once I understand that, think this way. If x value increases, then the denominator will increase. If the denominator increases, what will happen? The y value will decrease. And if x tends to infinity, what will y tend to? It will tend to 0. Agreed upon this? If the denominator becomes large, this ratio becomes small, y becomes close to 0. And it's not just true for positive infinity, but even for negative infinity, reason being you're squaring it. So 2 square is also 4, minus 2 square is also 4. So whether you square on right side, positive side, or square on the negative side, it's the same thing. So y value will go to 0. So when x is large, positive large or negative large, the y value is going to go down. That means this graph will look something like this. This is how it will look like at t is equal to 0. Everybody agrees upon this? Everybody agrees upon this? So what has happened? Let's rework. I thought instead of sketching the graph at any random time, let's sketch it at t is equal to 0. So substitute t is equal to 0. So you will get this as 9x square in the denominator. Next, if x is 0, y will become 5 by 2. 5 by 2 is 2.5. So this height obviously will be 2.5. Next, if x is large, 9x square is large, denominator is large, this ratio is small. So as the value of x increases, the y value reduces. That's what I have done. Everybody agrees upon this? Everybody? Yes, beast ever, I will be taking classes for the 11th to 12th moving batch, definitely. Now, once you got it, think upon the next point. The wave is going in the negative direction. So what would be the wave speed? Let's write it down. Okay, just 1 second. Okay, 1 second. Yes. So the wave is going in the negative direction. So the wave is going in the negative direction. So first of all, what is the wave speed? The wave speed, I just told you, it is the coefficient of the time term, upon the coefficient of the x term. Here the coefficient of the time term is 6, coefficient of the x term is 3, which is nothing but 2 meters per second. But which side? It is going towards left side. So in every 1 second, it goes 2 meters towards the left. So you can visualize it like this. After some time, this wave would have traveled like this. It would be traveling like this with certain velocity. Is everybody able to visualize this now? Why both sides, Tanishq? Simple fact, x can be positive number, it can be negative number, and it's a string. It will extend from left side to right side, both sides, right? So if I put x as positive or negative, the square value is same. So hence the graph is symmetric about the y-axis. Like a parabola, y is x square. Isn't it symmetric on left and right? Same way, because it is x square, it will be symmetric this side as well as that side. Understood? I hope this is clear. Very good. All right. Oh, looks like I have started the subtitles for some reason. Let me just probably get rid of this somehow. I don't know. 1 second. I'll just keep the, yep, just 1 second guys. Let me get back our presentation. Okay, there we go. Let's try this out. Okay, let's try this out on Desmos. Okay, let's see how does it look like. Okay, this is still going, but I don't want this. I want our graph, so which was 5 divided by, it was 2 plus, 3x plus 6t. Okay, and there was square over there. So I'll just put a square term right over here and see how does it look like. Okay, perfecto. Let's see now. I think I'll have to zoom out a little bit. Look at this wave. Look at this wave. It is traveling towards the left side. This is exactly what I had drawn. Do you guys see that, my warriors? Are you able to see that? Observe it on your screen right now. You can see it. Okay, can you see that? Just check this out. Perfect, isn't it? Sir, then the equation is not a wave equation. Nandini, who said wave equation should be only sine? If somebody has told you, they have definitely fooled you. Okay, that is not correct. Wave equation can be any equation which looks like this. Something x plus something time, some function of that. Sine is also a wave equation, cos is also a wave equation, exponential is also a wave equation, quadratic is also a wave equation. Even this is also a wave equation. You can see this pulse is traveling left side. That's all. Okay, sine equation is a special equation because it is like a sine wave. That's it. There is no other difference. Yes, I will be talking about phase difference and all of that, Adhika. Don't worry about it. All right. So let's move on to the next one coming up on your screen. So there we go. Just 1 second. Yep. So I hope this question is understood. So this is how you sketch waves. So you can have options which show the waves at different times or in different ways, and you have to choose and tick mark the correct option. How does the wave look like? So this is how it can come in an objective exam. Okay, here is another question coming up in front of your screen. So there's one change though. This square was supposed to be over here. This is very similar to our previous question. Let's see if we can solve this. With me everyone, show some josh, show some fire. I hope you guys are getting it. Let's do this. Disturbance of a wave propagating in the positive x direction is given by y is equal to 1 plus x square at time t is equal to 0, and at t is equal to 2 seconds it looks like this, where x and y are in meters. What is the shape of the wave disturbance does not change during the propagation? Yes, the shape keeps moving as it is. then what is the wave speed in meters per second? Observe this now carefully. At t is equal to 0, the wave equation is given by y is equal to 1 plus x square at t is equal to 0. But at t is equal to 2 seconds, the value of y is 1 upon 1 plus there is x minus 1 whole square. Okay, that raised to 2 is outside the round brackets, not the square brackets. This is how it looks like at t is equal to 2 seconds. Now, this should immediately click in your mind that yes, something is happening not in the numerator but in the denominator, and not everywhere, only where that x is. I know in general, the equation of a wave should be some function of ax plus minus bt. In this case, there is no mind. I don't know whether there is plus or minus. Let's figure this out. Okay. Now, observe this carefully, both these functions. This is at time 0. That means there is some t in this equation whose value has been substituted as 0. That's why you got this. There is some t in the equation, generic equation, where you have substituted the value of t as 2. That's why you have got it. But if you don't substitute any values at any time, how will the equation look like? The generic equation, it should be of this form only. Think carefully. 1 will be unaffected because nothing is happening in the numerator. This one and this one is also not getting affected when you put different values of time. So whatever is happening in this round brackets. Everybody understands this? Everybody understands this? Now observe. If I put x minus, okay, something x, but what is the coefficient of x over here? The coefficient of x is, okay, it is 1, and some b into t whole square. You will notice I can get this as well as this by substituting t as 0 or 2. How? Observe. Put time as 0, bt will become 0, it will just become x square. Can you see that? Everybody agrees to that? If I put time as 0 over here, I will get this. If you put some other value of time, which is 2 seconds, then you will get this. That means the only thing which I do not know is what is the value of b. I do not know what is the value of b. Now, think logically. This is at 2 seconds. This is at 2 seconds. So can I somehow find the value of b, guys? I think so. It's not that difficult. And the question is, what is the velocity of the wave? This is in 2 seconds. Come on, what should be the answer? Is it 2? Is it 4? Is it 0.5? Or is it 1? Think, come on, think about this. Here, if you go back to this yellow equation, the one in t is equal to 2 seconds, think by putting what value of b and what value of t will you get it as 1? Just compare these two, guys. Just compare these two. You will get this if 1 is equal to bt. If 1 is equal to bt, and the value of time is obviously 2 seconds. So from this you will get b is equal to half. And from here you will obviously get a, the coefficient of x is 1. That's it. Now you know the answer. What is the wave speed? Wave speed in general is b by a. That means it is half by a, which is 1, which is 0.5 meters per second, which is option C, I believe. Yes, it is option C. You can see that. Got it? It's just a matter of comparison, number 1. Number 2, manipulation, trying to figure out how would the actual wave equation look like and then doing the comparison. Yep, understood. Good evening, Kalyani. No, this is not wave optics. This is 11th standard waves. If you guys have not been taught all of this in waves, then you have been deceived. Okay, then you have very nicely been deceived, and they have skipped all the major parts of 11th standard waves. Okay, so let's move on to the next one, wavelength and all of these things. Wavelength, what is the meaning of wavelength? Wavelength is nothing but the smallest distance between 2 points of similar kind. Like say for example, this is a wave on a string. You can see this point over here and this point over here. Okay, these 2 points are of similar kind, so that is a wavelength. You can take 2 crests, that means 2 peaks, or 2 troughs, whatever you want, or you can take 2 points which are of same kind. You can take some point here and some point here also. Even these points will do. So it's the distance, minimum distance between 2 points of the same kind. That is called as a wavelength. Next, what is the meaning of frequency? Frequency is the rate at which a particle goes up and down. So when I say the frequency of a wave, it means the rate at which a particle is going up and down. That's it. Yep. Next, what is the meaning of time period? Time period is how much time does any particle on the wave take to complete one complete oscillation. So that's why I said oscillations is very much similar to waves, and without oscillations it will be difficult and tough to understand waves. And what's the relationship between time period and frequency? Well, that's simple. So this is as it is over here. So frequency is 1 by time period, and frequency is always expressed in hertz. You can also write angular frequency. Remember, I have spoken about angular frequency in SHM. So angular frequency of the wave will be nothing but 2 pi by t, which is also 2 pi f. And the unit of omega is a radian per second. So how many radians does it cover per second? That's the angular frequency of that wave. As simple as that. Okay, these are things which you should know. Next, velocity of a wave. Speed of a wave is different from the actual particle velocity. So when a wave goes, the speed with which it travels, the speed with which the energy moves is the wave speed, but the actual particle velocity is different. Don't get confused between that. And wave speed is given by this formula, which you might have studied back in 9th or 10th grade, or even in chemistry. Wave speed is frequency into the wavelength. Very, very important. Frequency into wavelength. And the speed of a wave, obviously I have just told you it is B by A. How is it determined? Very important chart. Look at this. The medium decides the wave speed. The medium decides the wave velocity. Next, the source. Okay, the source as in the person producing the sound, the person producing that wave. That person decides the frequency. So the frequency is decided by the source, and both of them together, depending on their values, decide the wavelength. So wavelength comes in the end, speed and frequency come first. So source decides frequency, medium, whatever is the material in which the waves are traveling, that decides your wave speed. Very, very important, and you can see that right over here. High frequency is more, wavelength is less. Frequency is less, wavelength is more. They are both inversely proportional to each other when the waves are traveling in the same medium. That means wave speed is fixed. Got it, my warriors? Perfecto. All right. Purvi has caught up with me. Very good. And now you feel that I'm talking very slowly. That's weird. I know. All right. Now talking about sinusoidal waves. See, this is the most important part of this chapter. Many things are just dependent on all these things. In general, I have told you how waves look like. It could be any form, like this one. This is also a wave. But a sinusoidal wave means a wave which looks like a sine or a cos. There are crests, there are peaks, there are valleys. So that's nothing but a sinusoidal wave. Let's draw or write a sinusoidal wave and let's see how does it look like. So let's just go to the another line and let's just write an equation. Y is equal to sine of, let's say, x plus or x minus, I don't know, t. Okay, look at this. This is a sine wave and you can see it is moving. Definitely it's a sine wave. There are peaks, there are valleys, and there is motion over here. Now, when we look at this sine wave, there are many aspects to it. Okay, let's just pause and observe. There are many aspects to this. Number one is, what's the amplitude? look at this. This is nothing but the amplitude. Let me just zoom onto this a little bit. Okay, perfecto. You can see now over here. Yes, this one over here is called as the amplitude of this wave. Amplitude. What's the maximum up or down motion of any particle? That's the amplitude. Next, you can see the wavelength. You can measure any 2 points of the same kind. Let's say if you want to measure from here to here, that's okay. So this is nothing but your wavelength. You can see that right over here. This is your wavelength. Perfecto. So these are the characteristics of a sinusoidal wave. And obviously there is frequency. That's the rate at which it is going up and down. All these things are there. Now let's see how each of these terms affects the characteristic of this wave. Let's get rid of this now. And let's try to change some number over here. Y is equal to sine of x minus t. Let's put a number like 2 and see what happens. Immediately you saw the height increased. Immediately you saw the height has increased. Let's make this number 2 as, let's say, number 5. Oh my god, it goes up till 5, comes down till minus 5. So clearly, what is this number doing over here? What is this number doing over here? It changes or affects the amplitude of the wave, the extent of the wave, which it goes up or down. So the amplitude is governed by this number which is there outside. Perfecto. Excellent. Got it? So let's all start defining the different terms of a sine wave. It's a repeating pattern. There are peaks, there are valleys. You can also call these things over here as crests, and these are called as trough. This is called as a trough. It's a smooth sine wave. Even a cosine wave will do, because sine and cosine at the end of the day, they are the same thing. So let's solve a question before going to the generic equation of the sine wave. There are two boats. They are anchored 4 meters apart. They bob up and down. That means they go up and down, returning to the same position every 3 seconds. When one of them is up, the other is down. There are never any crests or troughs between the boats. What do you think is the speed of the wave? It's a beautiful question. Let's see how many of you can visualize this and solve this within 1 minute. Come on, my warriors. I'm going to give you 1 minute time. Not more than that. Oops. Okay, let's start the time. Okay. So try to figure out how the diagram will look like. There are two boats besides each other. There are no crests or troughs between them. When one is up, one is down. What do you think is the speed of the wave? Figure this out. Come on, my warriors. Very, very interesting relationship. Think what should be the answer. Half a minute done. Okay. Two boats, they are anchored 4 meters apart. One goes up, the other goes down, and they go up and down every 3 seconds. Think, when one is up, the other is down, and there are nothing else in between. There is no other crest or trough in between. Then what do you think is the speed of the wave? Figure this out. Come on, my warriors. Okay, Puri saying D. Interestingo. Okay, Dakshin saying C, Ankit saying B, FF Gamer saying C, and the time is up. All right. Well, most of you are probably wrong. Very few people have got it correct. C option, very few people. Now let's see what the question actually means. See, when one boat is up, the other one is down. That means if the sea wave, it's traveling on the surface. Because of that, the boats which are besides each other, they are going up and down. They are going up and down. So when one boat is on the top, that means it's on the crest. The other boat is down, that means it's on the trough. And the distance between the boats is given to be 4 meters. But that's not the wavelength. Remember, wavelength is always the distance between crest to crest or trough to trough. So if this is 4, obviously from one crest to the other crest, the distance will be 8 meters. So the wavelength will be 8 meters. Everybody agrees to that? And we all know wave speed is lambda into f. Lambda is 8. frequency, it goes up and down at the rate of, every 3 seconds. So what's the frequency? I told you frequency is 1 by time period. Time period is 3 seconds. So this is 1 by 3. So what is 8 by 3, my warriors? It is 2.66666, which is nothing but 2.67 meters per second. Got it? Very good question. So you had to first understand if one is on the crest, the other is at the trough. So the wavelength will be double their distance. So that's why it will be 8 meters. Many of you would have taken it as 4 by 3. That will give you a wrong answer. Okay, the wavelength is not 4, it is 8. Moving on to the next one. So I just showed you how the amplitude of a wave can be changed. I just showed it to you over here. You can change this number and you can directly affect the amplitude. Guys, what if I make this number -3? Then is the amplitude 3 or is it -3? I just made the number as -3 sine x minus t. So it will go up and down again till 3 to -3. So is the amplitude 3 or is it -3? Put it up in the chat box. Come on, put it up in the chat box. Is the amplitude 3 or is it -3? Figure this out. Well, many of you might make a mistake, but I hope you don't make it. What is it? Is the amplitude 3 or is it -3? The amplitude is still going to be 3. Yes, it's not going to be -3. Amplitudes are all, no, it's not -3, it is 3. Amplitudes are always the positive, the modulus values. Amplitudes are not going to be negative. Keep this in mind, okay? So that is wrong. Next, let's change this over here and see what happens. Okay, perfecto. All right, so let's just play this and see what is happening. It's going towards the right side because there is a minus here. So let's make this number something else, maybe 2t. Okay, now it's going faster, but look at this particle over here at the origin. Just look at this particle over here. It's going up and down. If I change this number 2 to maybe 5, look at this particle which is over here. It is basically going up and down at a faster rate. Now, those of you who did not realize what this number could be, let me tell you what it should be right over here. Very simply put, just forget this x for a moment. For any given x, y will be some constant outside, which is like the amplitude, all right, and then, okay, just one second, amplitude and into sine of, some amplitude is there, sine of, for any given x, that means I have fixed x, some constant plus or minus 5 into t, for any given value of x. I'm getting y is some amplitude sine some constant plus minus 5t. What do you think this equation looks like? This resembles just like your SHM equation. Y is equal to amplitude, you can have sine or you can have cos, and then you have omega t plus phi. This phi is this constant over here and this omega is this phi over here. So the coefficient of time actually is nothing but the angular frequency of the wave. It's nothing but the angular frequency of the wave. So by changing this number, oh my god, what just happened? Okay, so by changing this number right over here, I can change the wave's frequency. Understood, my warriors? Perfecto. Now let's keep this number as constant and let's change this. What happens now? If I change this coefficient of x, let's say 5. Oh, the wave just got compressed. The wave just got compressed. Interesting. Let's change this number to something else, maybe 2. Let's see what happens now. Okay, now it has got expanded. So what do you think is the coefficient of x doing? The coefficient of x is actually changing the wavelength. It's actually affecting the wavelength. So do you guys agree this 2t has no role to play? This 2t has no role to play in the wavelength. It's only this coefficient of x which affects the wavelength. Look at this. If I make this 2 as 3, or if I make this 3 as something else, let's say 6, obviously the wavelength is affected by this number. So what's the relationship between the wavelength and this coefficient, it's very easy to observe that. Okay, let's just keep the graph as sine of x. Let's just keep the graph as sine of x. Okay, observe this. And let me mark it right over here. From this point till this point, like this is one complete wave, right? So from here till here, how much is this distance? One sine wave is completed in 2 pi radians. One wave is completed in 2 pi radians. So when x is 2 pi, it completes one complete cycle. Agreed? So right now, can I say that 2 pi is the wavelength right now when this coefficient of x is 1? Can you see that? Okay, let's make this coefficient something else. Let's make this coefficient something else. Let's make this as 2. Now think what will be the wavelength. Now if you guys are confused, ki, sir, what will happen now? I'm not able to measure it. Well, it's simple, guys. See, now there are two waves. Okay, just 1 second. 1 and 2. Two waves till 2 pi radians. There is one wave till only pi radian. Do you see the wavelength has now compressed to pi radians? Can you observe that, my warriors? Look at this. One wave is there only in pi radians. So now, does it make sense what this number is trying to do? Think carefully and let's write it down right over here. Now this is my new wavelength. So pi radians is the new wavelength. So if this 2 was something else, then what do you think the wavelength will be? It will be, think about it, 2 pi divided by that coefficient of x. Divided by the coefficient of x. If x is 1, lambda is 2 pi. If x is 2, then 2 cancels, it becomes pi. So it is 2 pi divided by the coefficient of x. Everybody understanding it? Got it? Perfecto? Yes. Excelente. So, what is this number called? This number over here is called as the angular wave number. What is this called? It is called as the angular wave number, and I just told you lambda will be 2 pi by k, or you can just shift k and lambda. K is nothing but 2 pi by lambda. If you are concerned about the units, the unit will be radian per meter. Radian per meter. This is very similar to omega. I just gave you the formula for omega. What was omega, my warriors? Omega was 2 pi by t, radian per second. So now I have found out two important characteristics of a sine wave. Angular frequency, that is the rate at which it is going up and down in radians. K is basically telling me how much is the wavelength. Radians per meters, it is 2 pi by lambda. If I know k, I can find out lambda. K is basically the coefficient of x. Is that clear? So we just discussed about amplitude. So let's write down the parameters of a wave. So in general, for a sinusoidal means a wave which goes up and down smoothly. There are crests and troughs. It follows the sine or the cosine equation. Sinusoidal wave, I can say that y is equal to a sine of kx plus minus omega t. I have told you what this plus minus means before only. So if it is positive, then it is going towards negative x. And if it is negative, it is going towards positive x. Next, I have also told you what omega is. This is your angular frequency, and this is of the unit radian per second. And this is nothing but 2 pi f. Next, k. What is k? This is nothing but your this is your radians per meter. So this is nothing but, I just told you, 1 second, I'll just write it down over here. Yeah, angular wave number, and this is nothing but 2 pi divided by lambda. This is nothing but radian per meter. And this one obviously is nothing but your amplitude. This is nothing but your amplitude. This is something which you should know. Fair enough. Are you getting a general idea of what a sinusoidal wave equation looks like? Now, is it necessary this should be sine? No. Even if it is not sine, this is okay. It can be cos also. You can also have a cos of omega t plus minus kx. This is also fine. There is no harm in that. There is no harm in that. Okay, sine or cos really doesn't matter. I put this up for you in printed form as well. And let's talk about the last term, which is called as the phase of a wave. Very, very important now. Phase. So let's go back over here. There is one thing which is missing, and I'm going to talk about it. Remember, in SHM also we had it. There was always some constant towards the end inside the brackets of sine or cos, which used to decide where does the SHM start from. The same thing is there over here as well. So let's get rid of this, and I can add one term over here called as phi. This phi, you can also put it over there if you want to. Okay, you can also put it over here. There is no harm in that. Okay, so plus phi is also wave equation. This phi is called as the phase constant of that wave. Now you might be wondering, what does it do? How does it affect the wave? I'll come to that. Phase constant is usually expressed in radians. Observe this graph in Desmos. You will get a hang of it. Okay, observe this. I'll just put the wave equation over here, minus something, 3t. Okay, and let's see how does the wave go. The wave is going towards the right side beautifully. That's how what we would expect. Okay, because there is a minus term inside. This minus is not necessary as such. Let's get rid of it. Now, imagine I put something like plus pi by 3. Now you will be like, sir, there is no change. It's still looking the same. There is no difference that I'm seeing. Okay, let's try some other number. Let's say pi by 6. There is no change at all. I don't think you can see any change over here. Then you'll be like, sir, what is that constant doing? Well, you cannot see what the constant is doing right now, but if you pause it, take a snapshot, then it will make sense. Let's bring it back to 0. Right now, the phase constant value is pi by 6. Time is 0. That means you have taken the photo at time 0. Observe this graph. This graph is not starting from 0. It's starting from some point right over here. Look at this. It's starting right over here. Why is it doing that? It's obvious. If x is 0, t is 0. If x is 0 at time 0, notice whatever is remaining inside is pi by 6. So sine of 30 degrees, which is pi by 6, is half. And half into 3 is 1.5. That's why this point is at 1.5 units. Now, let's try to change this and see what happens. Let's make this as pi by 3. Let's make this as pi by 3. Oh, this point has changed. It has gone to some other point because sine of pi by 3, sine 60 is root 3 by 2, and root 3 by 2 into 3 is approximately 2.598. Let's make this something else. Maybe pi by 2. Interesting. X is 0, t is 0. So sine of 90 is 1. So you can see y value is basically 3. So what exactly is this number doing? It's shifting the graph left or right initially. So it tells you the initial condition of the wave. That's it. It's just basically telling you where the wave was initially. That's all. Nothing else. Got it? So that's why it is called as a phase constant. So I'll just mention over here, it sets the initial conditions. Initial conditions. It sets the initial conditions of the wave. Perfecto. Now, the most important thing of a wave is also apart from the phase, one last thing which is remaining is the phase difference. Very, very important. Let's talk about the phase difference using, this graph itself. Let's get rid of this plus pi by 2. It's not needed. And let's play this simulation. Okay. So this wave is going towards your right. Okay. Now observe carefully. You will realize that the particles are going up and down, up and down. They are performing simple harmonic motions. Take any particle here is going up and down, up and down. Some other particle here is going down and then it's coming over here as the wave travels through that point. So each particle is going up and down. Do you think there are two particles close enough who are doing exactly the same thing, who are in sync, who are in phase, and I can say the phase difference between them is 0 or 360 degrees? Is there some 2 points? Are there some 2 points which are doing the exact same activity? And I think it is there. If you notice, 2 points on the crest or 2 points on the trough separated by a distance of wavelength, they will exactly do the same things as the wave travels. Look at that. Okay, as the wave travels, it will do exactly the same thing, those particles. That means those two particles separated by one wavelength have, no phase difference or 0 phase difference or 2 pi radians phase difference, or they are in sync or in phase. So going back to these slides. All right, let's go back. Okay, let me just make this. 1 second, guys. Let me bring this back. Okay. Yep. So going back over here, what does phase do? Phase changes the initial condition. And now we define a new term called as the phase difference. So observe this. I just mentioned two particles separated by lambda are basically in phase. But if there are two very close enough particles separated by some other distance, maybe their difference is something else. Maybe their difference is delta x. Then what is the phase difference between those two particles? It's very obvious. When the distance between them is lambda, they are in phase. That means 2 pi radians. When the distance between the two particles is delta x, what is the phase difference delta phi? What is the phase difference delta phi? That's the question. I repeat, when you have a wave like this separated by wavelength lambda, the phase difference between these two particles is 2 pi. But if two particles are separated by some other distance delta x, then what is the phase difference between them? Okay, let me just get your chats back, guys. Hold on. Yep, there we go. Yes, and I have your chats back. Yep. So the phase difference between them, use your unitary method and you will understand it very easily. For lambda, for wavelength, it is 2 pi. For delta x, how much it is? So obviously del phi will be 2 pi is per wavelength into delta x. This is your formula for finding basically phase difference between 2 points. Phase difference between any 2 points separated by delta x. Very, very important. No need of integration. It's just simple unitary method. Lambda distance, 2 pi radians. You can see that. Lambda distance, the phase difference between them, they both will be doing the same thing. So basically they are in sync. They are in sync. But when it is delta x, maybe some point here and maybe some point here. Now the separation between them is delta x. Now what is the phase difference between them? Now it will not be 2 pi, it will be something else. That will be given by this formula. Very good. So let's solve some questions so that you get a hang of it. Here is the first question coming up on your screen. Equation of a progressive wave is given by y is equal to 4 sine pi t by 5 minus x by 9 plus pi by 6. Which of the following is correct? Speed is 5, wavelength is 18, A is 0.04, N or frequency is 50 Hertz. Let's see how many of you can solve this question. Figure this out. Only one of them is obviously correct. Okay, let's try to do this question. First of all, if this is my wave equation, let's identify what and all parameters I know. Amplitude right from here is 4. And next, from here you can clearly see that the coefficient of t is pi by 5. Coefficient of time is nothing but omega. So omega is pi by 5. Next, coefficient of x is pi by 9. Coefficient of x is pi by 9 and that is also k. So k is nothing but pi by 9. Fair enough. Next, pi by 6, that is nothing but your phase constant. So phase constant is pi by 6. Now let's see what and all we can get from here. Amplitude is 0.04. No, amplitude is 4. So obviously option C is wrong. You can see that very easily. Next, omega is pi by 5. From this, I can figure out what's the frequency. Let's see if the frequency matches. This will be 2 pi into f. Therefore, f will be equal to pi cancels. 2 5s are 10. So look at this. F will be nothing but 1 by 5 into 2, which is 10, which is nothing but 0.1 Hertz. So obviously the frequency given over here is 50 Hertz. This is also wrong. I hope this is clear. Next, let's talk about the wavelength. How can I get the wavelength? From k. K is 2 pi by lambda. So let's just write it down. 2 pi by lambda. So pi cancels. From this, lambda will be equal to 2 into 9. 2 into 9, which is nothing but 18. Is 18 given? Yes, this is correct. So the wavelength is 18 meters. So that is definitely correct. Other things are wrong. Obviously, velocity will also be wrong. We can get to that. It's not that difficult. Remember, V was always coefficient of nothing but the t term upon coefficient of the x term. Here coefficient of t is always omega, coefficient of x is nothing but k. So it is omega by k. So just divide omega by k. You will get the answer. So pi by 5 divided by pi by 9. You will get this as 9 by 5. So 9 by 5 is definitely not 5. So this is wrong. So only option B is correct. Yes, option B is correct. Got it? So this is how you can solve questions based on wave equation. Trust me, the questions are actually very simple. It's not that difficult. Okay, moving on to the next one. It just looks scary, but don't get scared by it. A wave traveling in the positive x direction with this much amplitude has this much speed, wavelength is this much, then choose the correct expression for the wave. Let's try to figure this out. Amplitude is given, speed is given, wavelength is given. Now, we know the generic equation is y is equal to a sine or cos. You will have something kx plus minus omega t, or omega t plus minus kx, one and the same thing. Okay, you can also have omega t plus minus kx. Now, since it is clearly mentioned it is moving in the positive x direction, this word automatically eliminates one sign. So if it is positive, it should have minus sign. So clearly I can get rid of the plus sign over here. It should be of this form, guaranteed. Okay. Now, next, let's find out k and omega. That's not that difficult. Speed is known, wavelength is known. I can find out frequency. Okay, let's try to do this. V is equal to f lambda. V is 360. F, I don't know. Lambda is nothing but 60. So frequency is nothing but 6 Hertz. Now from frequency you can find omega. Omega is 2 pi f. So it will be 2 pi into 6. Same way you can also find the value of k, which is 2 pi by lambda. That means it will be 2 pi by wavelength, which is 60. So now look at the options and you can see the first two options have a positive sign over here. Obviously this is wrong, this is also wrong, because it is clearly mentioned it is going in the negative direction. So out of C and D, see which option is correct. Okay, in C option, 2 pi into 60. 2 pi into 6t. Yes, 2 pi into 6, correct. This is the value of omega. If you look at the value of k, it is 2 pi by 60. 2 pi by 60. C looks correct to me. In D option, it is just 6 pi, but actually it is 2 pi into 6. If you look at the value of omega, it is 2 pi into 6. Here it is just pi into 6. There is no 2 over there. So obviously D option is wrong. Yep, option C is correct. Yep, you can see that. Interesting question. Moving to the next one. A wave given by the equation this, what's the distance between 2 points having a phase difference of pi by 3? Where is the phase constant? Phase constant is 0. Okay, so the phase constant is assumed to be 0 because there was no option having phase constant, so we did not have to worry about it. Yeah. Now, if you remember, just previously I told you what is phase difference between any 2 points. It is 2 pi by lambda into delta x. In fact, I have a question on this right now. It says, what's the phase difference between the 2 points? What's the distance between the 2 points having a phase difference of pi by 3? So let's try to do this question. Here, del phi is given to be as pi by 3. Next, in order to find a distance between the 2 points, which is basically delta x, I need the formula. And what is that formula? I just gave you. Del phi is equal to 2 pi divided by lambda into delta x. That means I need wavelength. How do I get wavelength? Look at this expression. If you look at this expression carefully, you will realize this number 3 is actually the coefficient of x. That means it is k. So here k is 3 just by comparison. If k is 3, 2 pi by lambda is basically 3. And that's what I need, right? 2 pi by lambda is what I need over here. So let's try to substitute and see what do we get. 2 pi by lambda is 3. Del phi is pi by 3 right from here. Okay. Into delta x. So delta x will be pi by 9. Is pi by 9 there somewhere? Yes, it is there as option D. Got it? Yes, so that's how you get the answer. Pi by 9 is the correct answer. Beautiful question. Moving to the next one. Equation of a wave on a string, but there are two important characteristics that we are going to work on now. We have seen this just some time back. I have told you that any sine wave which is going on a string will look of this form. There might be some plus or minus sign. You can also have cos, you can have phi, that really doesn't matter. I am interested now to find out the velocity and the acceleration of a particle on that string. Meaning, look at this. This wave is traveling. As the wave goes, you will see after some time the wave will look like this. That means if you have a particle maybe here, it's going to come over here, from there to here, right? So from there to here. If it travels, it obviously has some particle velocity. And because it changes the direction, changes the speed, it will also have some particle acceleration. The velocity will keep changing, it will change the direction, magnitude. So velocity is also there, acceleration is also there. And these velocities are in the transverse direction. Transverse direction. Remember, this is completely different from your wave speed. Your wave was traveling here. This is the direction in which the wave is going. The particle's velocity and acceleration are in the perpendicular direction. How much will that be? To find that out, I'll use a simple trick. Remember, velocity is rate of change of position, but here position is given not in terms of x but in terms of y. So the position of this particle always changes with respect to y. Hence, all I will do is, let me just get rid of this. Okay. All right. Let's see if I can get it here. Okay, it just doesn't come. Okay, it came. Fine. So the velocity of that particle will be given by, think carefully, the rate of change of the y coordinate. That means it will be derivative of the y coordinate with respect to time. Correct. Now, when you take the derivative of this function, how will it look like? Let's see. So d by dt of a is a constant, comes outside, sine, you can have kx minus omega t minus kx, really doesn't matter. Kx minus omega t. K is a constant, x is a constant because you are differentiating with respect to time, not with respect to x. Only t is the variable. So when you take the derivative of sine, what will you get? Derivative of sine is cos. So you'll get cos of kx minus omega t, obviously. Next thing, whatever is the coefficient of t term will also come outside because of chain rule. So you will also get minus omega outside. This looks to me like a SHM equation. If position is a function of sine, then velocity is cos, then acceleration will go back to sine. So it's very similar to SHM. You can see this is minus a omega cos kx minus omega t. So this is your particle's velocity. And if you think carefully, you will realize that this number over here is the max speed of that particle, a omega, because cos has a max value of 1, least value of minus 1. So magnitude wise, a omega is the maximum speed of the particle, just like you had it in SHM, simple harmonic motion. Similarly, if you differentiate this, you will get the acceleration. So acceleration of the particle will be derivative of the particle velocity with respect to time. So let's try this out. A omega is a constant, so it will be just the derivative of the cos term. So it is kx minus omega t. So what will I get? Minus a omega. Derivative of cos is minus sign. Minus minus plus. So instead of cos, you will put minus sign, but that minus has cancelled out here. So kx minus omega t. But remember, the coefficient of time minus omega should come outside because of the chain rule. So put that minus omega outside. So it will now become minus a omega square sine kx minus omega t. So this is your acceleration of the particle. Yep, again chain rule. So now again you can see this part over here is your max magnitude of acceleration, a omega square, exactly like SHM. In fact, this also tells you one simple thing. All particles are performing SHMs. They are performing simple harmonic motions adjacent to each other, with some phase difference. I have given you that formula. Del phi is 2 pi by lambda into delta x. You can find how much is the phase difference between any two particles of a wave. So all the particles keep going up and down. They perform SHMs adjacent to each other. That's why it's very closely related to SHM. Let's move to some questions, my warriors. Here it is. We have a wave given by this. The max particle speed is equal to 4 times the wave speed. Very interesting question. What's the exact relationship between the wavelengths and the amplitude? Thank you, Arpit. So let's try to do this. I just mentioned to you all particles perform SHM. So if I have to find the max particle velocity, just think about the max speed in simple harmonic motion. What's the max speed in a simple harmonic motion? I just told you, and you know this from SHM, it is a omega. And what is omega? Omega is nothing but 2 pi by t. T is mentioned, 2 pi is also there, fair enough. This is 4 times the wave speed. Interesting. Wave speed, V, is coefficient of the t upon coefficient of x. Here coefficient of t, oh by the way, lambda t, everything is given, you know that v is always f into lambda, f is 1 by t into lambda, so that is, you know, the wave speed. This is 4 times of this. This thing is 4 times of v. That means it is 4 times of lambda by t. So think about it, what will happen next? So this is 2 pi into a divided by t. What and all will get cancelled? Look at this. What and all will get cancelled? T will get cancelled. This 2 and this 4 will get cancelled. So basically pi a divided by 2 is lambda. This is the expression we got. I just followed whatever was given in the question. Do I have something like that? Pi a by 2 is lambda? Yes, I have. Option B is correct. That's it. Done, done. So that's what I'm telling you. If you relate this with simple harmonic motion and you overcome your initial fear of equations, this chapter is just easy. I'll tell you, the best way to learn waves is via Desmos. If you're not using Desmos, then probably you are just by hearting things, you're not visualizing things. So use Desmos, play around with those equations, play around with those functions, play around with the graphs, see what it does. Trust me, you'll understand this chapter really well. That's why I've spent a lot of time explaining you all these things on Desmos. Show the shape of the wave at t. Oh, sorry. Shown is the wave. It should not be show. It should be shown as the shape of the wave at time 0. If the wave speed is 80 towards right, then find the wave equation of this wave. This is the wave which is shown at time 0. Okay, interesting. This entire thing is at t is equal to 0. The speed is 80 towards right. That means it's going like this with 80 units per second. So the question is, what is the equation going to look like? Let's try this out. Okay, let's assume that the wave equation will be of this form: a sine omega t minus kx plus or minus, but because it is going towards the right, it has to be minus. And there could be some phase constant as well. I don't know, this is at t is equal to 0. I don't know what's the phase constant. It could be pi, it could be 2 pi, it could be pi by 3, pi by 2. I do not know that. Let's figure this out. I don't know what is a, I don't know what is omega, I don't know what is k, I don't know what is phi. Let's find this out one by one. If you observe carefully, you'll immediately realize the height of this graph is 5 units. So basically this height is 5, that means the amplitude is 5. So quickly, the amplitude is 5. That's what you get right from here. This is nothing but the amplitude. Next, you can see the wavelength right from here till here. This is your wavelength. How much is the wavelength? The wavelength is 4. So k, which is 2 pi by lambda, will be 2 pi divided by 4, which is pi by 2. So k is pi by 2. Got it. Next, I don't know what is omega. How do I get it? I know the wave speed. From wave speed, I can get omega. I know the wavelength. So v is equal to f lambda, right? So wave speed is 80. Frequency, I don't know. Wavelength is 4. So f is nothing but 20. So omega will be 2 pi. 2 pi by 20. I hope this is clear, which is nothing but pi by 10. Everybody fine till this point? Everybody fine till this point, my warriors? Pakka? Very good, very good. Let's get moving then. Okay, now what is next? Okay, omega is known, k is known. The only thing I do not know is phi. Let's try to do this. When t is 0, this is time 0. If I put the value of x as 0, I should get the value of y. Interesting. When t is 0, at x equals to 0, you find out that the value of y is also 0. So let's try to put all these numbers in this equation and see what do you get. Y is 0, a doesn't matter, sine, I have omega t is 0, minus kx, x is 0, plus phi. So from this, am I not getting sine phi is 0? Am I not getting sine phi is 0? Now when is sine of phi 0? Think about it. Sine of phi, if it is 0, that means phi is either 0 or it is pi. Usually phase constants are between 0 and 2 pi radians. So I have two options out there. Two options out there, either it is 0 or is it pi. That's where many students make a mistake. They think if sine phi is 0, phi is 0 and they mark answer as 0. Wrong. I don't know that yet. I need to think which of them will go. Like, sir, both will be correct. Nah, come on. It's obvious. Either you put 0 or you put pi. Both answers are giving you the same thing. So why are you worrying about it so much? Nah. Now, here is why this question is tricky. This is at t is equal to 0, right? Think, how will the wave look like after some time? Just after some time, because it is going towards the right side. This wave will probably look like this. Look at this. This wave will probably look like this. So this is at t more than, this is a plus some delta. Okay, after 0 seconds, maybe 0.1, 0.2 seconds. Notice, what is this particle at origin doing? This particle at origin has gone on the top. This particle on the origin has gone on the top in some delta t time. Can you see that? The wave is going like that. So this particle has gone on the top. Everybody agrees? That means, can I say the velocity of the particle is upwards? That means positive. Positive y, negative y. So is it not positive? Everybody agrees to that? Everybody agrees to that? There is no denying this fact. Now, let's try to see what should be the particle velocity. If this is y, what should be the particle velocity? Take the derivative. A, sine's derivative is cos omega t minus kx plus phi, and the coefficient of t will come outside, so it will be nothing but omega. Okay, I just took the derivative. Vp is, I have got this by differentiating dy by dt. Dy by dt. Now, just substitute the value of x and t as 0 and then try to see what are you getting the value of velocity as. Just try to substitute and see what you get. So, at t is equal to 0, x equals to 0, Vp will come out to be a omega cos 0 minus 0 plus phi, which is a omega cos of phi. Now try to think. If you choose the value of phi as 0, the value of velocity, will it be positive or negative? Think. If you choose, if phi is 0, then Vp, is it positive or negative? Because that's what is going to matter. Cos of 0, 1. So Vp comes out to be positive. Fair enough. And if you choose the value of phi as pi radians, then what is the value of Vp going to be? Phi, if you choose it as pi, cos pi 180 minus 1, Vp will come out to be negative. But we know that when x is 0, t is 0, look at where the particle is going. It's going up. If it is going up, velocity should be positive, not negative. Hence, the correct solution will be when phi is 0. Hence, the final answer is as follows. Y is equal to A, which is 5, sine as it is, and omega. Omega is pi by 10. So pi by 10 t minus k. K value is pi by 2. And phi value is nothing but 0. So nothing over there. So this is our final answer. Done, done, done. What a brilliant question. It could have been pi also, you never know. What if the velocity was down? Then the answer would have been negative and this pi would be the correct answer. So it changes from question to question. Understood? What a brilliant question it is. Got it, my warriors? Shall we move ahead? Okay, here is the next question coming up on your screen. Guys, this lecture will be a little bit longer than I expected it to be. Okay, so hold on. Yep, we are going to continue till 9:15 or something like that, okay? I hope you guys are okay with that. And if you are hungry or if you have some other commitment, you can definitely watch the replay later on as well, but watch it because I have dedicated this time for you, all right? A transverse wave along a string is given by y is equal to this equation, x and y in centimeters, t in seconds, acceleration at x is equal to 4, at t is equal to 1. Okay, it's just all about equations. Let's try to do this. Because the question is about acceleration, that means you need to take the derivative of this function. So first let's find dy by dt. dy by dt will be 2, sine's derivative will be cos, and you will have 2 pi and 3t minus x and minus pi by 6. The coefficient of t is 3 into 2 pi. Beware, 3 and 2 pi both are there. So actually what will come out is 6 pi. 6 pi will come out. Okay, fair enough. Next, take the derivative of this also. So d square y by dt square will be 6 2s are 12. So 12 pi. Cos's derivative is minus. So minus sine. So minus sine 2 pi 3t minus x minus pi by 6. And then put the value of the coefficient of t, which is 2 pi into 3, which is again 6 pi right over here. So 6 6s are 36 into 2, which is 72. So it will be minus 72 pi square sine 2 pi 3t minus x minus pi by 6. So this is d square y by dt square, which is the second derivative, which is nothing but the acceleration. Now comes the actual question. At x equals to 4 and t is equal to 1. So x should be put as 4 and t should be put as 1, and let's see what do we get. So AP, acceleration of the particle, will be minus 72 pi square sine of 2 pi 3 minus 4, interesting, minus pi by 6. So 3 minus 4 is minus 1 minus 2 pi. Guys, any integral multiple of 2 pi doesn't matter. Remember, when you have sine of 2 pi plus or minus plus theta, it is same as sine of theta. Okay, this 2 pi, whether it is plus 2 pi minus 2 pi, really doesn't matter. So this will just become minus 72 pi square. All these numbers will not matter except for just minus pi by 6. Now pi by 6 is 30, sine 30 is half, but because there is a minus sign, sine of minus theta, remember sine of minus theta is minus of sine theta. That's a standard trigonometric formula, you would have learned it. So minus minus will become plus. So 72 into pi square, sine 30 is half. So this will be nothing but 36 pi square. Is that there somewhere? Yep, it is there. Option A is correct. No, there are no. Option A is correct. Okay. Raghav, even if you do not know much of 11th, it will be very useful, bacha, because 11th standard will also be revised. Number 1. Number 2, there are part tests. Number 3, there are assignments for 11th standard. Number 4, there is doubt solving available for all the syllabus. So you can get your doubts also cleared in live class, after the class also. So make use of that. Okay, perfecto. Let's move to the last part of today's session. I know it's an intensive session, lots of maths, and some of you might probably be scared of those equations, but trust me, when you use Desmos and when you play around with it over here, it should look a little bit simpler. Now, let's talk about the equation of a wave, but not for a wave on a string, but for sound. For sound, there is a small problem. The particles don't go up and down, the particles go back and forth. That's the problem. So let me show you a longitudinal wave right over here. Look at this. This is a longitudinal wave. Don't worry about standing waves and all that right now. And let me just play this for you and see how does it look like. Okay, I've just played it. This is a longitudinal wave. Observe any particle, or take this red line over here, or take that green line over there. These are particles which are going back and forth. The wave is going from one side to the other. The motion of the particle is in the x-axis. This particle has its mean position located somewhere, maybe this is its mean position. It is oscillating about that x value. So if you observe carefully, look at this particle. It goes from here till here. It goes like that. So if I choose over here, this particle, it oscillates between these 2 points. Maybe I can say this particle has some x coordinate where the mean position is located, and it oscillates over here. This particle oscillates over here. That means it also has some amplitude right over here. This would be the amplitude. I hope you can see that. This is the amplitude of that particle. Everybody agrees the amplitude will be either this way or that way. And at any instant, the particle's position will be a function of x and time. So this particle's position will depend on where you are, which particle you are talking. Am I talking about this? So it will depend on x, and it will also depend on time, because if I play this, the position of the particle changes with time. So the same thing, but a small modification for a sound wave. Observe now. Observe. Yes, the particle is performing SHM just like before. So going back to this over here. In case of a longitudinal wave, here is what I will notice and show. The particle goes back and forth like this. Goes back and forth like this. This one is the displacement, but max displacement. That's why I will call it as the displacement amplitude. And the symbol for displacement is S, and because it is the max displacement, I will call it SM, max displacement of the particle. This particle is probably, particle is probably at some position x. If I go to some other x, there will be some other particle performing SHM, and so on and so forth. Remember, this one over here is the mean position of such a particle, which is performing SHM, simple harmonic motion. When it performs SHM, obviously it will have some angular frequency, omega, which is 2 pi f. Now, at any instant, the particle will have some displacement. This is at some time. This will be the displacement. I will call it S. So S is basically instantaneous displacement of that particle, and this S will be a function. This will be a function of x comma time, just like before. In transverse wave, the y displacement was a function of x and time. Here, the displacement along x is a function of x and time. And if it is a sine wave, if you are singing or if you are humming a sine wave, a smooth crest and trough wave, then for sinusoidal, S will be just like the previous one. Instead of a sine kx plus minus omega t, here instead of a you will have maximum displacement, which is SM, and you will have sine kx plus or minus omega t. You can also have some phi over there. This is your displacement amplitude. This is your instantaneous displacement. Observe this via this simulation. The displacement will be a function of x as well as time. With time also it will change. SM is the maximum displacement. Everybody agrees to that? Got it? What this equation tells you? Very good. Now, once you understand that displacement is a function of x as well as t, where k is again the same thing, 2 pi by lambda, omega is 2 pi f, same things over here. One more thing that we need to talk about when we are talking about longitudinal waves, sound, is pressure. Very important thing. Observe this simulation. Look at the spacing between the lines. You can see the spacing is less here, that's a compression. The spacing is more here, that's a rarefaction. Compressions and rarefactions. Both of them will travel in that medium. And the pressure is also changing. And if I reduce the amplitude, the variations in the pressure are less. The displacement of the particle is also less. If I increase the particle's amplitude, you can see the variation in the pressure is also more. So even the pressure travels. But one more thing which I want you to notice, very, very important. Observe this. This is a very slow simulation. Look at any particle. I can probably speed it up a little bit. When the displacement is maximum on either side, okay, the pressure is very interesting. Look at this. When the displacement is maximum right now, that's it. When right now the pressure is not maximum. Now the pressure is maximum. That's when the velocity is maximum. Observe this change again. When the particle reaches on any of the extreme, now the pressure is not maximum. Now the pressure is maximum. That time the particle has maximum speed. That means pressure and displacement are not changing simultaneously. They are not in sync. They are not in phase. Do you see that? Observe again. Take the other extreme if you want. Okay, it's coming. Now is the extreme. The pressure is not maximum. Now the pressure is maximum, but the particle is already moving with very large speed. Now the displacement is maximum. Pressure was not maximum. And now again things have changed. So pressure and displacement don't go hand in hand. There is a phase difference of, think about it, when one is maximum, the other one is not maximum. Observe this. Now when the pressure is maximum, what will happen? Yes, look at this. The pressure is maximum, the speed is maximum. When speed is maximum, the particle will be at mean position. When speed is maximum, particle is at mean position. So when the particle is at mean position, that time the pressure is maximum. Maximum means extreme. Extreme means 90 degrees, plus minus 90 degree. So there is a phase difference of pi by 2. Pi by 2. Got it? Look at it carefully. Observe this. Very interesting. Very interesting. Look at this. The time when this compression is completely the red line is completely inside the compression. Look at the red line when it completely goes inside the compression. See where it is and what it is doing. Not now, but now. Yes, it is going with maximum speed. Maximum speed occurs at mean. And compression, that means max pressure. Max pressure, mean position. So pressure is maximum, but displacement is 0. Understood? Pressure is maximum, but displacement is 0. Do you see a phase difference? They are not in sync of pi by 2. I hope this is clear. That is what is very, very important. Let me just go back. So if this is the displacement, then when I talk about the pressure, observe this. The pressure, okay, oops, 1 second. Okay, the pressure changes, okay, over and below, okay, over and below. 1 second, guys. Oops. Over and below the normal or the atmospheric pressure, meaning these variations are there only because the sound is moving. If sound was not there, pressure will be same everywhere. Hence, the actual pressure at that point, will be atmospheric pressure plus the changes in the pressure. This is because of the sound. This is because of the atmosphere. This delta P will be varying with x as well as time. The variations in the pressure are going to change. The pressure will be sometimes maximum, sometimes minimum, sometimes it will be atmospheric pressure. So this is also going to be a sine cos function. But I just told you that there is a phase difference of 90. That means if this is sine, this will be cos function. If this is cos, this will be sine function. So if this is displacement by sine, this is a cos function of kx plus minus omega t plus phi, and the constant over here is Pm. This is the max variation in the pressure. This is also called as the pressure amplitude. Very, very important. What is this called? This is called as the pressure amplitude. Meaning, think of it this way. Okay, let's put it in a simple way. Observe this. Imagine at some point, this is pressure and I don't know, this is maybe time. Let's say there is no sound at all. If there is no sound, pressure will be constant. This will be P naught, which is atmospheric pressure. This is when there is no sound. When there will be sound, then the graph will look something like this. This is your compression. This is your rarefaction. High pressure, low pressure. This value, the max variation, this is your Pm. This same Pm over here. Notice the pressures are changing over and below the atmospheric pressure. So this delta P is telling you the instantaneous excess pressure above the atmospheric pressure. Instantaneous value of that excess pressure. Are you guys getting it now? When and where do we need to use phi? You will need it when at t is equal to 0, the wave starts in some weird position, or basically you can see that wave has been shifted by some amount. That's when you need it. Is that understood? Very, very, very important. So what is this value? The max variation is pressure amplitude. The instantaneous value is that delta P over here. That delta P is also called as the excess pressure. Okay, I'll just put it over here. This is just called as the excess pressure. This is over that, atmospheric pressure. You might be wondering, is there any relationship between this Pm and this Sm? Yes, there is. And you don't have to know about the derivations and all of that, but let me just give it to you. So Pm, the pressure amplitude, is BKSM. Very, very important relationship. Pm is this Pm, pressure amplitude, Sm is displacement amplitude, B obviously is your bulk modulus, which I have studied back in solids. K is your standard angular wave number. So very important. If displacement is more, pressure variations are also more. That's what it says. And we just saw that right over here. If displacement is more, then you will see that pressure variations are more. But if amplitude is less, then you can see that the pressure variations are also less. So as you increase the amplitude, that's when you will notice that the pressure variations are more. I don't know why it's changing. This should not change, guys. Amplitude on its own. Oh my God, this amplitude itself is performing SHM. This should not have happened. Okay, perfecto. Let's move to some questions. Okay, all of this will be there in your PDF. You can download the PDF later on. Okay, PM is BKSM. Very, very important. Okay, a sound wave is propagating in air. It may be treated either as a displacement wave or as a pressure wave. I just showed it to you. Displacement wave or as a pressure wave. I think Gokul Nath was talking about this. This is what your displacement wave is, bacha. All right. So I didn't want to tell you that time because obviously you will get confused. Right now, I hope you understand the difference between a displacement and a pressure wave. So when the particles are going back and forth and you're looking at the displacement aspect of it, that's the displacement wave of the sound. But at the same time, pressure is also changing. So when you look at that aspect, you can treat it like a pressure wave. Compressions and rarefactions are passing on. Okay. Now, what do you think is the phase difference? Yes, it is 90 degrees, standard. I just showed it to you right over here, right? If one is sine, the other is cos. If this was cos, this will be sine. Always 90 degrees, they do not go hand in hand. Next question. If the pressure variation is as shown over here, 10 raised to 5 plus minus 14 Pa sine this is a pressure wave of amplitude 10 centimeter. What is the bulk modulus? Okay, let's try to do this. Try to compare this equation with your original pressure equation. I told you pressure at any point is atmospheric pressure plus that excess pressure, and that excess pressure is nothing but your Pm, and you have sine, and then you have Kx plus minus omega t. You can also have omega t minus Kx also. I think over here omega t is first, so it's okay. You can also have sine of omega t plus minus Kx. This is also fine. Okay, this is also fine. Either this or this, or. Now compare these two, you will quickly realize which one is what, and you can immediately figure out what the bulk modulus is. Remember, I just gave you the relationship between bulk modulus, angular wave number, Pm and Sm, and I told you Pm is Bk Sm. Remember this very easy relationship. Pm is Bk Sm, standard relationship. Do I know the value of Pm? I think so. I can compare it and figure it out. Look at this. This 14 is same as Pm. 10 to the power 5 is P naught. Atmospheric pressure is in 10 to the power 5. So quickly you can say Pm is 14 pascals. Next, I need K. So compare it and see what the value of K is. K is nothing but from here pi. Fair enough. Sm is given 10 centimeter. So Sm is 10 centimeter, which is 0.1 meter. This was a radian per meter. The only thing remaining is the bulk modulus. So let's try this out. It's not that difficult. So let's start substituting everything and see what do we get. 14 will be B into K. K is pi, so just put pi over here, into Sm, the displacement amplitude, which I just got it as 0.1. So therefore, B will be equal to 14 divided by 0.1 into pi, which is nothing but 140 divided by pi. So is it there somewhere 140 by pi? Yes, it is there. But obviously this will be in pascals in SI unit. As simple as that. Yes, Dharan, correct. Option C. Very good. So it's that simple. It's that simple. It's just a matter of patience and perseverance and visualization till some point. After that, it's just remembering these formulas. There is nothing great about these equations. So here are some questions for your homework. First question for your homework, second question for your homework, third question for your homework, and fourth question for your homework. Solve this and I'll be seeing you guys next time. And remember, tonight is the last night of the Republic Day sale. So if you want 50% off on all the courses, go ahead, buy it right now. Yeah, maximum discounts. Tomorrow, that's after tonight, 12 o'clock, the offers will close down. And even if you use my coupon code, you will get offers, but it will be the best offers as compared to any other offer, but it will not be the maximum best offer on account of the Republic Week sale which is happening. So make sure you make the best use of this. All right, thank you very much. And you can find all the crash course link, the Vedantu Pro link, it's all there in the description box below. Go ahead, check it out, join it. If you have any doubts, leave it in the comment section. Bye bye, take care, have a great time, have your dinner. Thank you for tuning in. This was Shreyas here, your captain. Hasta la vista.